that, especially like for the first data set, almost like 20% higher than the. So this is the benchmark performance on the latitude prediction using the first data set. And the y-axis shows the ground truth latitude, and the x-axis shows the predicted latitude. And the observation is that if you just check a single model like GPT 4.1, so you can observe that when the model is confident about its output, it's generally correct, like for GPT 4.1, right? So like those red points just falls into the diagonal line. And in comparison, Gemini 2.5 Pro is super confident. Prior to this slide, you can see, you can just observe a very clear, very densely cluster in the middle of the figure, right? But for the longitude prediction, there is a cube-like box in the middle, nearly across all the models. So what does this mean? So I think one possible explanation is that because for latitude prediction, generally the large language model can capture the environment cues. So for example, like in some higher latitude, like in the north part of in the United States, the tree types in the north part and the south part could be quite different. Like the palm tree generally appear in the south part, but the palm trees do not appear in the north part of the United States. So large language model may capture those environmental cues when identify the location from the image. But for longitude, there's no clear environmental cues for large language model to identify. So when large language model is not very sure about the prediction, so generally just randomly guessing the outputs. So this also explains why for the longitude prediction, you can see the prediction is quite like follow a uniform distribution, right? And these are some explanations we can think about to explain the difference between longitude prediction and the latitude prediction. And the boundary, the cube-like box, the boundary actually is the border of the United States of the longitude in the longitude. And when plotting the geospatial patterns, we also observe some very interesting patterns. So if you just look at the accuracy for each state in the United States, despite like Llama generally just show very low accuracy, but for like Gemini and GPT, the geospatial pattern is really interesting. So the red color means that the accuracy is higher, and the blue color means the accuracy is lower. So you can observe that some specific states like California, Washington, Texas, and Florida, and New York. So these 5 states generally show some higher performance than other states. I think one very possible explanation is because these 5 states, they're really using the regression model. So the for this figure is the log value, so that can measure the importance of the features, and the y-axis is the so you can see nearly across all of the subplots, nearly all of the models strongly store environments while consistently penalizing rural, natural, and indoor scenes. So if an image like taken in some rural place, and then it's very likely large language model cannot identify the street image tends to signals. I think it's probably because like if a picture is taken on street, there might be like some street signs and business names that appeared on the shops. That can help, those textual cues can help large language model to identify the location. But like if the image is a general scenery, then maybe it's really hard, it's really challenging for large language model to correctly identify the location. So these are some of the key takeaways. And the predicted line is quite close to each other over the study period. So based on this observation, we can layer, and the bottom 4 figures shows the prediction with the geospatial awareness layer. So you can see actually across different models. And we also actually do a comparison between using large language model. One is the GPT-03 mini. So you can see like for 03 mini, the MAE and the RMSE is quite smaller than other models. And the other one that we found the performance is quite outstanding, the GPT-5 mini. Also, the performance is quite consistent across all the 5 wildfire events. And this is the daily cost prediction. Also, like GPT-03 mini and GPT-5 mini, they show some better performance as compared to other models. And next, we also did a feature importance because for the geospatial awareness layer, we retrieve different types of information from the GIS database, such as the weather, resource, containment, infrastructure, demographics, and terrain. And like for the daily personnel prediction, we found that the terrain attributes actually plays the most important feature in contributing to the successful prediction. But for the daily cost, we found that it's really model dependent. So like GPT-5 mini still like labels like terrain as the most important the factor. But for other models such as like GPT-3, so you can see the variance actually, the weight is quite more evenly distributed across these features. So these are some of the key observations for the second project. And for the last project, we try to use large language model for some sudden onset pre-event impact simulation. So we choose earthquakes as the study object. So the conventional earthquake impact assessment, such as the remote sensing, on-site investigation, and survey response. So remote sensing actually takes the satellite or aircraft based sensors and take some images from the air and then use some computer vision technology to identify the impact. And then for on-site investigation, they observe their surroundings, how they feel about the shaking level from the earthquake. But all of those traditional methods, they are actually just do the impact assessment of the event happen. And for some earthquake, especially like for earthquake, because it's happened all of a sudden, it's very different from like hurricane or wildfire or other geospatial events. Earthquake just happen all of a sudden. It's really hard to do pre-event simulation. So the most popular applied methods for pre-event simulation is the ground motion models. But ground motion models cannot identify how people might perceive the risks. Like for the did you feel map, actually this is really human centered. This just describes how people feel about the earthquake in a place. So driven by this ideal, we are really curious to test whether large language model can simulate how humans perceive the risks before an event occurs. So based on this ideal, we try to build different agents. Like for each agent, for example, we feed the simulated agent a lot of like information in that place. So for example, like where this person might live, like the geolocation information, like the city, the coordinates, the distance from the epicenter, the geospatial features, like the VS30. So VS30 is used to measure the site condition, which is a very key geospatial feature to predict the seismic risk, and also the socioeconomic and demographic. And before I dive into the result, modify Mercalli intensity scale to indicate how people feel about the shaking levels during the earthquake. And then for the study, we choose two data sets. So one data set is for the 2019 Ridgecrest earthquake, and the magnitude of this earthquake is 7.1 magnitude of 2019 Ridgecrest earthquake is much higher than the other earthquake, but the damage that the earthquake caused to the local communities, to the local areas, is much smaller compared to the other earthquake. One of the reasons is because the earthquake happened in a place where the population density is very small. So most people that live in these, like live in Los Angeles or the or like the Santa Cruz, they're not affected. They can feel the earthquake, but they're not physically. They can feel the earthquake, but they do not observe many damages in their surroundings. So we feel these two earthquakes could be really representative for our study because you can see, although one earthquake is the magnitude is higher, the damage is actually much lower. So we want to test whether large language model can capture this impact if we just simulate the agents. So, and then we design the research framework. So for the first step, we randomly select some data samples. We use the stratified samples for each zip code. So for each zip code, we randomly generate like 50 samples. And for each sample, you can consider it and also the socioeconomic factors, including the population density, the age, the income, and education. And last is the street view images. So you can see there are multiple types of data that can fit into each sensor. And then we also design the prompt engineering and then design the experiment, including like the model selection, prompt techniques, ablation study, and the performance evaluation. And then for the evaluation metrics, we firstly calculate the average estimation using all of the simulated sensors in a zip code area. And then we can calculate the average estimate for given the zip code or county level. And then we use the root mean square error to calculate the difference between the predicted value and the ground truth value. And last, we also use the correlation coefficient to see how the predicted value, how the trend of the predicted value aligns well with the ground truth value. So these are some of the evaluation metrics that we use in this study. So here are the results. So this is the simulation results for the 2015 Napa earthquake. So you can observe that so the star sign means the epicenter of the earthquake. And so you can observe that for area that close to the epicenter, especially for those several counties close to the epicenter, they experience some heavier impact and the level 7 the seismic impact. And then for counties that further from the epicenter, you can see the MMI, the predicted MMI is much lower. So you can see the color is actually lighter. And this is the simulation result for the 2019 Ridgecrest earthquake. So you can see the epicenter is far from the densely populated areas, and then the damage close to the epicenter is very heavy. And then for areas that farther from the epicenter is much, the damage is much smaller. So this is the simulation for the 2019 Ridgecrest earthquake. So you can clearly tell the difference by comparing these two maps, right? And then I think one very interesting observation when we do the experiment is we are also curious to know, is it possible that large language model just learn the information? So actually, we did several data leakage tests. So one data leakage test is we set the earthquake happen time in the future, not in the past. And then we also hide the location of the epicenter. So So large language model does know where the earthquake happened. But we found the simulation results is also very similar to the simulation results. So like for table 3, so you can see this is the experiment results on data leakage. So for the right-hand side, it showed the simulation without the location information. And for the result on the left-hand side, showed the simulation result with the location information. But you can see the simulation result is quite similar to each other. And then across different models, we also have several interesting observations. So one interesting observation is that like for the first, like 2014 Napa earthquake, we observed that Qianwen 2.5 32 billion model generate the best prediction performance. But GPT-4o at the time of the experiment generate the highest correlation. But one very interesting thing that the higher RMSE does not always result in higher correlation, and also higher correlation might not result in higher RMSE. This observation is quite interesting because sometimes we find the overall prediction could be deviated from the ground truth values, but large language model can actually capture the comparison, especially the comparative relationship between different places. So this can explain why sometimes the RMSE is higher, but the correlation is actually not that high. And this is the city level simulation results for different cities using different large language models. So you can see this is the actual average MMI, and these are the predicted MMI by large language models. And these are the the count of the sensors that we randomly generate for each city. So this is the pre-simulation performance for the city level simulation. And okay, so based on these 3 projects, I want to summarize some key findings. So like for the first project, the image geolocalization, we actually observed that closed source models always lead in the performance, but also at a higher cost. And models rely on different visual cues, but they might not generate a holistic understanding. And for the second model, we find that, okay, by feeding large language model with the geospatial information, that can help large language model to outperform both physical and machine learning baselines. And we also found the integration of the spatial and temporal cues within the geospatial awareness layer can improve the prediction performance. But the features are different importance. And the last topic, we find that, okay, the large language model simulation shows somewhat good alignment with the real world USGS deduced field map. We also found the simulation performance depends on model type, size, and input information. But at the same time, I think for my today's presentation, I just put a lot of emphasis on like large language model have a lot of potential for this spatial intelligence, but actually at the same time, we also find a lot of limitations. So for example, like for the first project, we have observed that large language model shows a lot of bias in the image geolocalization, right? Especially for those less populated areas. The performance decreased a lot compared to those populated areas. And then for the second project, although for some wildfire events, we find that, okay, by feeding the geospatial information, that can help improve the large language model prediction performance. But we also found in other events, the prediction performance is not that satisfied. So we find that the performance is actually not very consistent. And we are still trying to find some good explanation to explain why the performance vary a lot. And like for the last simulation, we also find that although the correlation might show some alignment with the real world observation, but you can observe that the absolute prediction actually could be deviated from the ground truth values, right? But the correlation is good. And the other thing we also did some analysis in our paper by trying to identify whether large language model can capture the information, like the location information. We do find that when the simulated pipeline, the agent is far from the epicenter, large language model can actually capture that information. Actually, when the distance between the simulated place and the epicenter increases, actually the simulated impact decreases. That's good. But at the same time, we also found large language model is not very sensitive to some geospatial features, such as the site condition that I mentioned, which is very important for the seismic risk prediction. But we found that large language model can actually cannot capture the relationship between the prediction values and the site conditions. So at the same time of showing the potential of large language model for the geospatial intelligence, I also want to mention their limitations by performing the geospatial tasks. And in the end, I want to share some takeaways and future opportunities. So for the first lesson that we learned from this project is that if we want large language model to have good geospatial intelligence, we really need to integrate some specialized domain knowledge. So this is like what we have shown in our second project. When feeding the proper information into the large language model, it can help enhance the large language model prediction. And the second lesson that we've learned is that we really need to come up with a way to mitigate the geographic and environmental bias, especially for those maybe less resource places or areas. And the next lesson that we learn is that how to unify the heterogeneous data sources is very key. It's a very key lesson in the geospatial tasks. The reason is because geospatial data generally exist at varying scales and granularities. So bringing those diverse data sets into a unified framework is really important to enable consistent analysis. And the last point that I want to share is that we really need to make the spatial reasoning explainable. So we need a system to not just output a prediction, but output the very reasonable and consistent reasoning process to support its prediction. And this could be very important for the downstream tasks and help the decision makers to bridge the decision-making process with the reasoning process. And so these are all the lessons that I want to share in my today's presentation. And I want to thank again for all the audience for taking time to listen to my presentation. Now I want to open the floor for questions.
Thanks so much, Neil, for the very informative talk. It's super interesting. I really learned a lot from your talks. Previously, I have not too much knowledge on this specific topic, but I feel it's super interesting and very impactful. And I do have lots of questions, but maybe we can start from some questions from our audience online.
Yes.
I guess there's one audience asking. I guess in the first of your talk, in the first work you
Yeah.
mentioned, I think you are using some large language model self-reported certainty score, right?
Yes. It's confidence score.
Right. Yeah. So basically, I think the question is like why you choose it. Like, for instance, is it reliable? Like how you design it?
Yeah, so this is a really great question because I know there are a lot of studies in large language model trying to investigate the relationship between the confidence levels and the prediction accuracy, right? So the reason is because we feel those images they have different visual cues, and some of the visual cues they're really clear. So like for example, there are like some like street signs or business names. So that can really help the model confidently output a location for its output. But for other images, like the second image, it's just like a really random image taken from anywhere in the world. So we want to use this confidence level to guide the large language model to like feel how confidently it is about its output. Because for some of the images, it's really hard to identify the vision cues. And that's the reason why we integrate the confidence level into the reverse geocoding process. And we actually find some interesting observations, like for some model like GPT 4.1, when GPT 4.1 is super confident about its output.
Mhm.
And generally, the output is correct. And when GPT 4.1 is not very confident about output, and generally those output are
Yeah.
not. Yeah, but we also find like O3 and Gemini 2.5, as I mentioned in the presentation, we find that like O3 is generally not very confident about its output. But if you compare the performance across these two models, the confidence level does not play any importance on its accuracy because the accuracy is quite close to each other. Like O3 is
Mhm.
not confident, but Gemini 2.5 is super confident, but the accuracy is pretty close. Yeah.
Yeah, super interesting. I guess we also observe similar the confidence trend in other scenarios, right? So basically,
Yeah.
it's very different across different models. That's super interesting. And also, I guess another audience is also asking, like, still in the first project, I guess
Yeah.
you are using some regression methods, right? So
Yeah.
basically, I think the question is about, is that for the baselines or what kind of thing? Could you please add more information on this part?
Yeah, this is a really great question. So the original idea, so why we build this two regression model is because we try to quantify the reasoning process. Because generally, large language model can output like a description of its reasoning, right? But it's really uncertain why large language model can do this very challenging task because the image geolocalization is not easy. It involves a lot of analysis regarding the visual cues, a lot of the environmental cues. So we are very curious to know why large language model can identify those factors and what factors if a large language model can correctly identify, that can contribute significantly to the to the success geolocation process. So that's why we build the regression models. So we can consider the why. So like for the first model, we consider whether large language model can correctly identify the city level information. And then we put all of the information that large language model extract from the image at the dependent features. And then we put all of the dependent features and the output feature into the regression model. And then we can calculate the coefficient and the p-value regarding each feature, regarding each input feature. So through this way, we can quantify the importance of the input feature and quantify the reasoning process. Like for example, like from the feature importance analysis, we found that when large language model can identify the street information or the urban information or the outdoor information, and then it's very likely large language model can correctly can correctly identify the geolocation from an image.
Yeah, super cool.
Yeah,
Hope this clarifies the audience online's questions. I also have some question about your first work because I think it's super interesting, but maybe my question is a little out of the scope. I'm just wondering, I'm pretty sure there's definitely some work on the trustworthiness about this geolocalization, right? Because I
yeah,
mean, um, like we can see the larger model has a very strong ability to do this kind of geolocalization, but I guess there maybe also have some concerns on privacy. Like if I just upload a picture of myself with some background, maybe the model can also know where I'm from. So basically, I mean, do you have any thoughts on this? Like, did you try to, or maybe there's some research on this topic. Like, is there anything to do this kind of um, preserve this kind of privacy, like not make these models to know like the exact location of a specific person.
Yeah, I think that's a really interesting topic, and thank you so much for proposing this question. And especially, I think because we just come back from the NeurIPS, I think I
Mhm,
also
mhm,
learned a lot. A lot of people they're trying to um, build some methods that make the large language model incapable of doing the things, right? Because like
mhm.
for
Yeah,
example, if we just feed the large language model a image, there are a lot of like privacy information, and we don't want large language model to learn from those private information. I would
exactly.
definitely think about how we can make large language model incapable of doing this. Yeah.
Yeah, I fully agree. Maybe this is some interesting future work because I'm also thinking about something about maybe we can also do some adversarial robustness, right? Like for
Yeah.
instance, if you put the Eiffel Tower in front of the
Yeah.
image, but the background is from another country, so will you fool the model to know like what is the location is? So maybe this is some interesting thing we could do.
Yes, I agree. Yeah, I totally agree. I feel that's a really interesting direction to explore in the future.
Cool,
Yeah.
interesting. And also like I guess maybe your second work or something you mentioned like I guess you also use LM agents to do this kind of um thing, right? Like the wildfire prediction or to have some output based on this different scenario. I'm just wondering, did you test the latency of this kind of agent? Because I guess in some cases, like it has to be react in real time, right? Like you
Yes.
cannot wait for a long time to the model to retrieve lots of things, to think a lot. So I'm just wondering how it real works. Did you test it in some real world scenarios or some systems?
Yeah, I believe in our original paper,
Yeah.
especially because we just submitted this paper and we also received some similar feedback from the reviewers. And also
Mhm.
one reviewer asked us about the latency because like exactly like you
Okay.
say, like for some disasters, it require really fast response. And
Mhm.
we add the latency, and I couldn't remember the exact number, but for each case, like for each um, days prediction, I believe it just at most it just takes several, maybe like 10 seconds or 20 seconds. I can't
Okay.
remember the exact
Mhm.
number, but not that
Cool.
long. Yeah.
Cool. I got it. Got it. Then
Yeah.
that I guess that may be very useful in real world systems to do the real time reaction, I guess.
Yeah, yeah. You know, one very interesting observation also from the second project is that we
Uh-huh.
find in some cases when feeding the large language model with different types of geospatial information, it can increase the performance. But also in a few events, especially regarding the cost prediction, we found that feeding the geospatial information can decrease the performance a little bit.
Mhm. Oh,
Yeah,
that's super
so
interesting.
yeah, so we are still wondering maybe large language models still have some challenges in understanding the relationship, especially between those numerical factors.
I got it.
Yeah,
Super cool.
yeah. Thank you so
And
much.
also have yeah, super cool. Thanks for the answer. I think that's super interesting. And also I also have some questions for your third work. I think it's
Yeah,
also very interesting. So I just wonder, like, I guess to use the retrieval augmented, right? Like
yeah,
to retrieve from some extra knowledge. I just wondering, did you check like what kind of knowledge being retrieved? I mean, for instance, is it based on the how should I say, like the geographical property of that area, or based on some earthquake report, like some same properties of the earthquake, records. So I'm just curious about this. I have no
yeah.
knowledge on this. Mhm.
Yeah, you're exactly correct. Actually, you get the right answer. So we build a retrieve data set. So using because for the simulated data set, so we just create a lot of like sensors across different places. And then for the retrieve data sets, we just build the sensors in other places. And then when the large language model to retrieve the information, just compare the similarity like between the site condition, the
Hmm.
distance, the population density, and also the education, the street view by compare the similarities between the simulated area and also the
Okay,
ground truth value from the retrieved data sets, and then make a prediction.
I got it. So basically, it's a fusion of this all different kinds of information, right?
Yes, and we found that actually the RAG system can significantly improve the simulation performance.
Okay, cool. Did
Yeah,
you observe like which one of them is most being retrieved? For instance, did they mostly based on geospatial or something else? I'm not pretty sure.
yeah, I need to check that. Yeah, I need to
Okay,
discuss with
cool. No
my
worry.
another colleague. Yeah,
Yeah, no worry. And also, I also have one question about this project is that I think you are using the I think you call the DYFI reports, right? So basically,
yeah,
it's reported by a user. Like for instance, how do they feel about the scale, and how
yes,
do they feel about the psychological panic, right? So
yes,
I'm just wondering, how should we understand like if we use LLM to do this kind of simulation? I mean, um, maybe I missed some parts of your talk, but I'm just thinking like whether we should say we are using LLMs to simulate real physical damage, or we are just using it to simulate the humans' perceived panic, or
yeah,
it's a combination of both. Like I'm not
yeah.
pretty sure.
Yeah,
Mhm.
that's another very great questions. Yeah, so basically we just simulate how the people perceive the risk. It's not a real physical damage. It's not. It's
Okay.
just based on how people feel about the shaking level of the earthquake.
Mhm.
So we firstly got some ground truth values from the did you feel map. So basically in the ground truth survey, so they provide an estimate. It's not an estimate. It's a real value reported by users who feel the earthquake. So it's an aggregated value in a region, like in a zip code.
Mhm.
And we use that value reported by users, aggregated value reported by the general public at the ground truth. And then we simulate. So you can see from this conceptual framework, you can see that we just simulate a lot of human sensors in different places. And by feeding those information into the human sensors, like say, hey, I live in this place, and here are the features of my surroundings, and then there would be an earthquake happen like maybe like 200 kilometers from my place, and how would I perceive the shaking level in my current place. So this is totally simulation. This is just to simulate how people perceive the shaking level of the
I
earthquakes.
got it. I got it.
Yeah,
Super interesting.
thank you so much.
Actually, I still have lots of questions, but I think we are already on time. So maybe let me ask one more last question. So maybe it's a very high level general question. So I think you are expert in doing this kind of geospatial intelligence. I'm just thinking like, what do you think is the most bottleneck of the current research? For instance, do you think it's because of the model lack the knowledge of understanding the physics world? Or do you think is it because we do not have very, very high quality data to train them to learn this kind of intelligence?
Yeah, I think that's a really great question because I want to go back to my first question, like
Mhm.
the title of the presentation, right? Do large language model really have the geospatial intelligence? I feel it could go in both ways. Although large language model have shown some potential, in other cases, actually, large language model also show a lot of limitations and biases. Like the one challenge, as you mentioned, is the training data, right? Especially as we
Yeah.
observed, like for the first project, like for some places, the accuracy is actually quite low. Like for this figure, right? Like
Yeah.
for those like really resource intensive places, like really densely populated area, the population, the
Mhm.
accuracy, the performance accuracy could be quite high. But for like the middle places in the United States, you can see nearly all of the models just show really low accuracy. So I guess one of the reasons is because large language model, the training data might reflect the real world data. It's because
Yeah.
people just live in those places. So like for those like less populated area, maybe large language models performance could be really terrible. So I think this is one challenge for large language model to understand the geospatial tasks. And another challenge, I think this is not restricted to the geospatial tasks. This restrict
Mhm.
to this just apply to all of the tasks that involve in the numerical process, because we still find it also like in the geospatial tasks, large language models sometimes are also not very good at processing especially the large tabular data, because the relationship between the features could be quite complex. So large language models are not very good at processing this data, these high dimensional features. So I feel this could be another challenge for a large language model to understand the geospatial intelligence.
Exactly. Actually, I fully agree. I think
Yeah.
this is maybe not special to this specific topic, right? So it also applies to other areas. And we see like different researchers have different solutions. So probably, I mean, larger model probably is not the final solution. We still need some new architectures and new models.
Yeah, I
Cool.
agree. Yeah, if the audience have more questions, please just feel comfortable to send me email and I will answer them.
Yeah, definitely. Thanks a
Yeah,
lot, Liao, for the nice sharing again. And also thanks for everybody for coming. As Liao said, if you have any questions, please email Liao and also you can reach out to us. Thanks again. Wish you have
yeah,
a
thank you
good
so much for
weekend.
the invitation. And I hope everybody will have a great weekend.
Thank you. Bye-bye.
Thank you. Bye-bye.
OK，我这里结束了，可方那边结束了吗？
那边已结束了是吧？我看一下。
大家就虽然惊心动魄，但是还可以。
还是已经突破了。哎，所以那边是已经结束了吗？我先把我的外闭了，我看一下。